Good morning, class, and welcome to this lesson on Geometric Optics 2, Spherical Mirrors and Focal Length. Today we will be able to describe the two types of spherical mirrors and give the equations for their focal length. Okay, so what is a spherical mirror? We basically have two types of spherical mirrors. We have concave and convex. So imagine right now I have a sphere right here, and it is a mirror. Okay, it is a spherical mirror. Crazy name. On this spherical mirror, the reflective side can be on the outside. It could be reflective on the outside, or it could be reflective on the inside. Okay? And so what we're going to be doing is we're going to be looking at a piece of this spherical mirror. So this right here, this mirror that is curving inward, this piece of the mirror is that. Okay, so we're taking a piece of a mirror and saying it at one point was part of a bigger circle, and by assuming it was part of a circle, that helps us with our math. Okay, so a spherical mirror is a mirror that is curved that was part of a sphere before. Okay, so we have a concave mirror and a convex mirror. Concave, kind of just like it sounds. Concave is caved in. Notice the reflective side is on the inside here, and so it sends light rays inward. It sends light rays inward. It's concave. It's like it's caving in on the light ray that's coming, okay? Convex is kind of like curved out. I don't have any cool sayings for that. It's just curved out. So it's curving outward, and so when a light ray hits it, it's going to head outward like that, okay? And another thing we want to define here, as you can see in both these pictures, is the principal axis. The principal axis. The principal axis is the line running through the midpoint or the center slash radius of curvature slash radius of curvature. So what does that mean? Let's take this spherical mirror right here. Let's make a 2D version of it right below it. So we have a 2D version of the spherical mirror. And remember, we are only looking at this piece right here. We're looking at this piece of the mirror, and this is the center of the circle right here. So we're going to call this the center of curvature or the radius of curvature. They're the same thing. AP uses R. A lot of books use C. It doesn't really matter what you use. Just know that capital C or capital R is talking about the center right here. And so if we draw a straight line through that center and then in this mirror, this is the principal axis right here. So here's the principal axis. Here's the principal axis. So let's talk about this concept of focal length and focal point. When a light ray hits a concave mirror, its light is going to hit and it's going to come to a certain point. Whether it's up here or it can even come from down here, it's going to reflect and come across this point, which is called the focal point. So the focal point is the point where light converges. This is the point where light converges, okay? It's all going to come across this point right here. And the focal length is this length right here. The length from the focal point to the mirror, okay? The focal length is the length from the focal point to the mirror. So that is the focal point. However, we have an equation for this focal point, very, very simple one, but I want to show you where it comes from. Okay, so we have a light ray that is coming in and hits this mirror. Okay, we have a light ray that's coming in, it hits this mirror. Now, because this is a circle, because this is part of a sphere, remember we said from earlier, the angle of incidence equals the angle of reflection. Well, and this angle, if we looked at a plane mirror, like this angle is the angle away from normal. Okay, this is the normal line. And for a flat mirror, this is a very simple line to understand. It's just perpendicular to the mirror. But what is perpendicular to a circular mirror? Well, a circular mirror, the normal is going to be the line that passes through the center of curvature or the radius of curvature or the center of the mirror. So remember that we have this point C. If we look at this whole spherical mirror here, we have this point C. It's the very middle. Okay? the normal is going to pass through that. So if light is coming in parallel and hits the mirror, this is the normal line. So this angle of incidence is going to equal the angle of reflection. This angle of incidence is going to equal this angle of reflection. And it's going to pass through this focal point right here. And as you can see here, we have a picture here. This blue shaded area is an isosceles triangle. Isosceles triangle. It's an isosceles triangle because it has two of the same angles. So if these two angles are the same, then that means these two distances are the same as well. This distance is exactly equal to this distance. And what we know from experience is that if the angle is small, it doesn't work for large angles, but if the angle is small, this distance right here, the distance from, in this diagram, the displacement from C to F is equal to the displacement from F to B. So from F to B, this is the same distance as from C to F. Okay? So what does that really mean? That means F is at the midpoint from C to B. F is at the midpoint. And if it's at the midpoint, that means that our focal point, our F, is equal to 1/2 C, or 1/2 R. And this is going to be our equation. And for the purposes of this class, AP Physics, it's always going to be this equation right here. I don't think they're going to give you any sort of example which has a very large angle and it's not passing through the focal point. I haven't seen it, so I could be wrong, but I haven't seen it. So our focal point is going to be 1/2 the radius of curvature. Okay, it's going to be the midpoint between the radius and the mirror. And here's an example of some dishes. These are solar panels, and the sun comes in, hits the dish, and these are reflected. You can tell this is like a concave mirror, and these are reflected to this point right here. And so inside these bars is some sort of oil or liquid, and this heats up, and that helps us gain energy. But what I'm trying to show you with the satellite dish is at this point, this bar in the middle right here, this is at the focal point. Or if you have a satellite dish at your house for TV, you might recognize it looks something like this. Well, this thing in the middle is the receiver, because you get radio, or you get waves from the satellites. It hits the dish, and these reflect back and hit the focal point where the receiver is located. So the receivers are all located at the focal point. Okay, so those are some good examples of a concave mirror, and this example of the focal point. Now, we have a convex mirror here, okay? And as you can see, it's a little bit different. In a convex mirror, we have rays coming in, and they're going to be reflected outward. They're going to be reflected outward. So unlike the concave mirror, there's no focal point on this side. But if we drew the extension of the reflected rays, the focal point would be 1/2 the distance, the center of curvature, just like before. So F is equal to 1/2 R, just like before. But we're going to call this negative 1/2 R. And there's not a negative number here. Negative just denotes that it's behind the mirror. And you will see in later videos this concept of negative and positive coming up a lot. So, so the focal point for a convex mirror is going to be negative 1/2 R. Negative because the focal point is behind the mirror, not in front of the mirror.